Module 8, DeviceNet Deep Dive, Byte-Level Real-Time, CAN-based, the network that knows its job. This module exists to correct a very common misunderstanding. Many engineers hear DeviceNet and think, open quote, oh, that's just a smaller Fieldbus, close quote. That assumption is wrong and dangerous in design decisions. DeviceNet does not exist to compete with Fieldbus. It exists because Fieldbus is often too much for the job at hand. This episode is about why DeviceNet was created and when it clearly beats Fieldbus. Why DeviceNet exists. The gap Fieldbus never meant to fill. Let's start with industrial reality. Most plant floor devices are not. Flow transmitters, PID loops, process instruments. They are motor starters, drives, proximity switches, photoelectric sensors, solenoid valves, barcode readers. These devices don't need complex function blocks, distributed PID execution, rich multivariable messaging. They need, open quote, fast, reliable exchange of small amounts of data repeatedly, close quote. That's the gap DeviceNet was built to fill. The tutorial is very explicit about this positioning. DeviceNet is aimed at byte-level transfer of information, especially for on-off devices, drives, and discrete equipment. Thinking. The core design choice DeviceNet is not bit-level like sensor buses, and it's not message-heavy like Fieldbus. It lives in the byte-oriented sweet spot. That means more expressive than a single on-off, less complex than full process messages. A single DeviceNet exchange might carry status words, control commands, fault codes, speed references, device health bits. That's exactly what devices like drives and starters need. Nothing more, nothing less. Why CAN was the perfect foundation DeviceNet is built on CAN, Controller Area Network, a technology originally designed for automotive systems. That choice tells you everything. CAN was designed for real-time behavior, noise immunity, harsh environments, distributed devices, fast arbitration without collisions. The tutorial highlights this clearly. DeviceNet uses CAN bus chips, benefiting from massive production volumes and low cost. In other words, use-real chaos. CAN already knew how to survive it. Producer-consumer, not master-slave thinking. One of DeviceNet's most important ideas is producer-consumer communication. Instead of one device requesting, another responding. DeviceNet allows a device to produce data, multiple devices to consume it simultaneously. This is hugely efficient for status device coordination, reducing network load. One transmission feeds many listeners. That efficiency matters when updates are frequent and timing matters. Why DeviceNet beats Fieldbus in certain applications. Let's be very clear here. DeviceNet beats Fieldbus when control is device-centric, not loop-centric. Data size is small but frequent. Real-time response matters. Cost and simplicity matter. The devices are drives, starters, sensors, not analyzers. Fieldbus shines in process plants, analog control, rich diagnostics, distributed control strategies. DeviceNet shines in discrete manufacturing, machine control, packaging lines, automotive-style automation. Trying to use Fieldbus where DeviceNet belongs is over-engineering. Trying to use DeviceNet where Fieldbus belongs is under-engineering. Power communication, a practical win. Like other device networks, DeviceNet allows power and communication on the same cable, reduced wiring, faster installation, cleaner panels. But unlike H1 Fieldbus, DeviceNet is not power limited to ultra-low speeds. It balances reasonable baud rates, practical cable lengths, enough power for typical devices. This makes it extremely attractive for OEM machines and skids. The mental model to lock in. Here's the clean way to remember DeviceNet's purpose. Fieldbus asks, how do we control a process? DeviceNet asks, how do devices behave together, quickly and reliably? DeviceNet doesn't try to be everything. It tries to be exactly enough. And that restraint is why it has survived and thrived in the environments it was designed for. Now that you understand why DeviceNet exists, the next step becomes obvious. How does it actually move data so efficiently? And what communication mechanisms make that possible? That's where cyclic I/O, change of state, and explicit messaging enter the picture, and where DeviceNet's elegance really shows. Hashtag CAN at the core plus DeviceNet layering, why it's cheap, fast, and still industrial. This episode is about inheritance. DeviceNet didn't invent its reliability. It borrowed it very deliberately from CAN. And once you understand what DeviceNet takes unchanged from CAN and what it adds on top, its cost advantage and real-time behavior suddenly make perfect sense. CAN, a network born in chaos and perfected by it. CAN, Controller Area Network, was not designed in a clean laboratory. It was designed for cars, engines, vibration, electrical noise, safety-critical behavior. In other words, environments that look suspiciously like industrial machinery. The tutorial makes this clear. DeviceNet is built directly on CAN hardware and protocol foundations. Inheriting its robustness and arbitration mechanisms explains half of DeviceNet's success. What CAN gives DeviceNet for free? Let's be precise about what DeviceNet gets from CAN without reinventing anything. 1. Deterministic arbitration without collisions. CAN does not use CSMACD, it uses bitwise arbitration. Multiple devices may try to transmit at the same time, but the highest priority message wins, lower priority nodes back off automatically. No collision destroys data. This means no wasted bandwidth, no retries, no randomness. Real-time behavior emerges naturally. 2. Message-based identity, not address-based. In CAN, messages are identified by IDs, not by sender-receiver pairs. The ID represents what the data is, how important it is. This aligns perfectly with producer-consumer thinking. One producer, many consumers, zero coordination overhead. DeviceNet inherits this directly. 3. Built-in error detection and recovery. CAN nodes constantly monitor bit errors, frame errors, acknowledgement errors. Faulty nodes detect their own misbehavior, reduce participation, can remove themselves from the bus. This self-policing behavior is why CAN networks fail gracefully, not catastrophically. 4. Massive silicon economy of scale. Here's the quiet killer advantage. CAN chips are produced in hundreds of millions for automotive use. DeviceNet rides that volume. The tutorial explicitly notes that DeviceNet benefits from low-cost CAN chipsets due to automotive industry scale. Danza for dinner. This means low e-silicon, proven reliability, long-term availability. Industrial vendors didn't have to invent hardware. They leveraged what already survived cars. Where DeviceNet starts. Adding its own intelligence, CAN by itself is powerful, but incomplete for industrial automation. DeviceNet adds the layers CAN never tried to solve. Physical layer, industrialized CAN. DeviceNet defines cable types, power conductors, shielding rules, connector standards. Unlike raw CAN, power and communication share the same cable. DeviceNet standardizes trunk drop topology, installation becomes repeatable. This is where DeviceNet stops being electronics and becomes plant ready. Data link layer, still pure CAN. Here's an important insight. DeviceNet does not replace CAN's data link layer. It uses CAN framing, CAN arbitration, CAN error handling, unmodified. That's why timing behavior remains so solid. Chat application layer, where DeviceNet becomes useful. This is where DeviceNet adds real value. It defines object models, device profiles, parameter structures, explicit versus I/O messaging, configuration behavior. This layer answers questions CAN never asked. What is a drive? What is a starter? How does a sensor expose status? How does a device report faults? Without this layer, CAN is just a transport. With it, DeviceNet becomes plug-and-work capable. Why this layering keeps cost low? Here's the architectural genius. DeviceNet reuses CAN silicon unchanged, adds software-level standardization, avoids heavy protocol stacks, avoids TCP/IP complexity, avoids controller-centric scheduling across it. That means smaller processors, less memory, faster startup, lower power draw, which directly translates to, open quote, cheaper devices that still behave predictably, close quote. The industrial design philosophy you should recognize. DeviceNet follows a very disciplined philosophy. Let CAN handle time and arbitration. Let DeviceNet define meaning and structure. Don't add layers unless they solve a real problem. That restraint is why DeviceNet feels lean, deterministic, predictable, affordable. It's not underpowered, it's right-sized. The mental model to lock in. Here's the clean takeaway. CAN provides real-time physics. DeviceNet provides industrial semantics. Low cost doesn't come from cutting corners. It comes from standing on the shoulders of a technology that already survived hell. And now that you understand the CAN foundation and DeviceNet's layering discipline, the next question naturally follows. How does DeviceNet actually move I/O data efficiently, cyclically, on change, and on demand? That's where its real elegance shows up in day-to-day machine control. Producer-consumer, why one message can feed an entire machine. This episode is deceptively important. On the surface, producer-consumer sounds like just another networking term. In reality, it explains why DeviceNet stays fast even when lots of devices are talking, and why older request-response thinking collapses under load. If you understand this model, you understand DeviceNet's efficiency at a gut level. The old mental model: request, response everywhere. Most engineers grow up with this instinct. Controller asks a device for data, device responds, controller asks the next device, repeat, forever. This is request-response thinking. It feels orderly, it feels controlled, and at small scale it works fine. But let's look at what actually happens on a shared network. If 10 devices need the same status, 10 separate requests go out, 10 separate responses come back, the wire fills with duplicated effort. The network is busy, not with information, but with coordination overhead. That's the hidden tax of request-response. DeviceNet's question was different. DeviceNet didn't ask, open quote, how do I let a controller pull devices faster? Close quote. It asked, open quote, why should the same data be sent 10 times? Close quote. That question leads directly to the producer-consumer model. Producer-consumer, data has an owner, not a requester. In DeviceNet, data belongs to the producer. A device produces a piece of data, places it on the network, and does so without being asked each time, though. Any device that needs that data simply consumes it. No handshake, no individual request, no duplication, one transmission, many listeners. That's multicast efficiency by design. Why CAN makes this model natural? This model works so cleanly because of what DeviceNet inherits from CAN. In CAN, messages are identified by what they are, not who sent them. Arbitration already prioritizes important data. All nodes see all messages and decide locally what matters. So when a DeviceNet device produces data, the message ID tells everyone what it represents. Consumers already know whether they care, no coordination is required. The wire doesn't need to know who's listening, only the meaning of the message matters. Bandwidth savings. The math engineers appreciate. Let's do this practically. Imagine, one drive produces speed feedback, 5 other devices care about that speed: controller, HMI, logger, safety monitor, diagnostic tool. Request-response world, 5 requests, 5 responses, 10 frames per update. Producer-consumer world, 1 produced message, 5 consumers listen, 1 frame per update. That's not an optimization, that's an order of magnitude reduction in traffic. And because DeviceNet traffic is often cyclic and frequent, this difference compounds fast. Hashtag determinism improves as traffic drops. Here's the part many people miss. Producer-consumer doesn't just save bandwidth, it improves timing predictability. Fewer frames means less arbitration pressure, less queuing, less jitter, more stable update intervals. So real-time behavior improves without increasing speed. That's classic industrial design. Open quote, don't go faster, go cleaner, close quote. Change of state fits perfectly with this model. Producer-consumer pairs beautifully with change-of-state behavior. A device can produce data only when it changes, or at a defined cyclic rate, or both. Consumers don't care why it arrived. They just react when it does. This avoids constant polling of static signals, wasted bandwidth on unchanged data, artificial traffic just to check in. The network carries meaningful change, not ritual. Why controllers love this model? From a controller's perspective, it doesn't manage polling schedules, it doesn't chase devices, it reacts to data as it arrives. Control logic becomes event-aware, cleaner, less timing fragile. The controller stops being a traffic cop and becomes a decision engine. The mental model to lock in. Here's the sentence I want you to remember. Request-response asks devices for data. Producer-consumer lets data announce itself. DeviceNet chose the second path, and that's why it scales gracefully on busy machines. Once you internalize this, DeviceNet's behavior stops feeling different and starts feeling inevitable. And now that you understand how DeviceNet saves bandwidth, the next question becomes practical. How does it decide when to send data? Cyclically, on change, or on demand? That's where I/O messaging types complete the picture. Communication types in DeviceNet: poll, strobe, cyclic, COS, explicit. Pick the mechanism that matches the data. This episode is about discipline. DeviceNet doesn't assume all data behaves the same, because in real machines, it doesn't. Some data changes constantly. Some barely ever moves. Some only matters when something goes wrong. So DeviceNet gives you multiple communication mechanisms, each optimized for a type of data behavior. Choosing the wrong one doesn't just waste bandwidth, it destroys determinism. Let's walk through them the way a machine actually breathes. Start with the rule. Most engineers miss. Before we name any mechanism, lock this in. Open quote. Data behavior decides the communication type, not convenience. Close quote. If you choose based on habit, we always poll, DeviceNet will feel slow and crowded. If you choose based on behavior, it feels effortless. Polling. Controlled, predictable, controller-centric polling is the most familiar pattern. The controller asks a specific device for data, the device responds, the exchange repeats on a schedule. This is explicit control. Polling works best when you need guaranteed updates, you want the controller in charge, the device count is moderate, timing predictability matters. Typical uses: drives, starters, devices requiring regular supervision. The downside is obvious. One request per device, one response per device, bandwidth scales linearly with node count. Polling is disciplined, but not efficient at scale. Strobe. One question, many answers. Strobe is a clever optimization of polling. Instead of polling devices one by one, the controller sends one broadcast strobe. All devices respond in a predefined order. This is useful when many devices share the same simple data. Data size is small, synchronization matters. Classic example, discrete I/O blocks reporting status bits. Strobe reduces controller effort, but responses still consume bandwidth. It's efficient for simple, uniform devices, not rich data producers. Cyclic. I'll tell you every n milliseconds. Cyclic I/O flips the thinking. Instead of being asked, a device produces data automatically at a fixed interval, whether it changed or not. This is perfect when data must be refreshed regularly, consumers depend on constant updates, timing consistency matters more than efficiency. Typical cyclic data: speed feedback, position, process variables used in control. Cyclic messaging trades bandwidth for predictable freshness. You always know, when the next update arrives, how stale the data can be. Change of state, when silence means stability. Change of state is where DeviceNet shows real elegance. A device produces data only when it changes or when a defined time limit expires. Heartbeat. This matches reality beautifully. Most machine states sit idle, remain steady, only matter when something changes. CoS shines when data is event-driven, updates are rare but important, bandwidth must be conserved. Examples: limit switches, fault flags, mode changes, alarms. CoS avoids flooding the network with nothing happened messages. The wire carries meaning, not reassurance. Explicit messaging, conversations, not I/O. Now step out of real-time I/O entirely. Explicit messaging is used for configuration, diagnostics, parameter access, device identity, non-time critical data. These messages are request response, larger, slower, acyclic. And that's exactly what they should be. Explicit messaging is not meant for control loops, it's meant for engineering interaction. Trying to use explicit messages for cyclic control is a classic beginner mistake. The bandwidth reality. This is the engineering part. Here's the practical hierarchy. From most bandwidth efficient to most bandwidth hungry. 1. CoS, only when something matters. 2. Cyclic, steady, predictable load. 3. Strobe, bursty, simple devices. 4. Poll, disciplined but linear scaling. 5. Explicit, necessary, but kept off the fast lane. DeviceNet works because it lets you mix these intelligently. Control data rides one path, configuration rides another. Diagnostics never block real-time traffic. How engineers get this wrong and pay for it. Common mistakes: polling everything for safety, using cyclic for static data, sending diagnostics cyclically, treating explicit messages like I/O. The result: congested buses, missed updates, jitter, DeviceNet feels slow complaints. DeviceNet isn't slow, it's honest. It gives you enough rope to either engineer well or hang your bandwidth. The mental model to lock in. Here's the sentence that ends confusion. Choose the communication type based on how the data behaves when nobody is watching. Constant change, cyclic. Rare change, CoS. Simple group status, strobe. Tight supervision. Poll, human interaction, explicit. Once you design with that lens, DeviceNet stops feeling complex and starts feeling surgical. And with that, you now understand not just what DeviceNet is, but how to make it behave beautifully under load. From here, the remaining questions are practical ones. segment limits, power budgeting, network design trade-offs, which is exactly where real projects live. DeviceNet physical network rules where most mysterious failures are born. This episode is pure plant floor truth. DeviceNet rarely fails because the protocol is wrong, the controller is confused, the software is buggy. It fails because physical rules were treated as suggestions, and DeviceNet is not forgiving about that. This is where we lock in the discipline that keeps byte-level real-time networks stable instead of flaky. Start with the reality check. DeviceNet is CAN-based, multi-drop, power communication on the same cable. That combination is powerful and electrically demanding. You are not just designing a network. You are designing a distributed power system with real-time data riding on it. Once you see it that way, all the rules suddenly make sense. Trunk drop topology. One highway, many short ramps. DeviceNet uses a trunk and drop topology. Trunk equals the main backbone. Drops equals short connections to individual devices. This is not optional structure. It's what keeps signal integrity and timing intact. Why this matters. The trunk is impedance controlled. Drops are intentionally short to avoid reflections. Every extra meter of drop adds capacitance and distortion. Long drops don't fail immediately. They fail under load at higher baud rates when one more device is added, which is why they cause the worst kind of problems, intermittent ones. Termination. Exactly two. No negotiation. DeviceNet requires exactly two terminators, one at each end of the trunk, never on drops. These terminators match the cable impedance, absorb signal energy, prevent reflections. Common mistakes: missing one terminator, adding terminators at devices, leaving factory-installed terminators enabled everywhere. Any of those will distort CAN arbitration, create retries, cause random node dropouts. If arbitration breaks, determinism dies, and DeviceNet lives on deterministic arbitration. Baud rate versus distance. Physics always collects its debt. This is the rule engineers remember, but don't always respect. Higher baud rate equals shorter allowable distance. Typical practical limits: 125 kilobps longest trunk lengths, 250 kilopad medium distances, 500 kilobps short compact networks. This is not conservative design, it's electrical reality. CAN arbitration depends on all nodes seeing the same bits at the same time. If the network is too long for the baud rate, arbitration breaks, priorities fail, errors explode. Slowing down often fixes mystery light issues instantly because timing margins return. Node limits. It's not just addressing, yes, DeviceNet supports a fixed maximum node count, but the real limit is rarely addressing. It's power budget, cable voltage drop, startup current, ground reference stability. You can hit power limits long before protocol limits. Adding one more device can drop voltage below tolerance at the far end, cause brownouts during startup, trigger cascading communication faults, which is why power calculations are not paperwork. They are network survival math. Power integrity, the silent killer. This is where DeviceNet punishes shortcuts because devices draw power from the network, voltage drops along the trunk, current adds up fast. Rules that matter: use correct cable gauge, size power supplies generously, consider worst-case startup current, segment the network if needed. A DeviceNet network that works until everything starts at once is not healthy. It's living on borrowed voltage. Pack grounding and shielding, discipline not decoration. CAN is robust but not magic. Proper grounding ensures stable reference for transceivers, noise rejection, shield effectiveness. Common mistakes: grounding the shield at both ends, floating grounds across cabinets, mixing power, earth, and signal reference carelessly. Result: ground loops, noise injection, arbitration errors that look like software bugs. Ground once intentionally and consistently. The failure pattern. You'll start recognizing, once you've seen enough DeviceNet systems, a pattern becomes obvious. Random dropouts, termination, or grounding. Works at low load, fails at high power budget, works short, fails long, baud rate versus distance. One device causes chaos, drop length, or startup current. These are not protocol mysteries, they are physical violations. The mental model to lock in. Here's the sentence that prevents 80% of DeviceNet problems. DeviceNet is a real-time power distribution system that happens to move data. Respect that, and arbitration stays clean, timing stays deterministic, devices behave predictably. Ignore it, and the network lies to you. Problems move around, commissioning turns into superstition. Once you design DeviceNet with electrical discipline instead of hope, it becomes one of the most stable and cost-effective device networks ever built. And with that, you've completed the full picture. Why DeviceNet exists, how it communicates, how it stays fast, and why the physical layer decides everything on it. That's real industrial networking mastery, not just familiarity with acronyms.